So we reviewed inverse variation yesterday, and today we want to start talking about rational functions. A rational function is when you have a ratio, a fraction, with a polynomial in the numerator and a polynomial in the denominator. So unlike inverse variation, where it's just a number in the numerator and x is in the denominator, we're dealing with a combination function. It's called a composite function. So we have inverse variation, but we're combining it with polynomial functions. And what happens is it starts to take on the characteristics of both the inverse variation and the polynomial. So notice for this particular function, we have x plus 4 in the numerator. That's a linear function. And 2x squared minus 13x minus 7, a quadratic function in the denominator. So together, that's a rational function. It's a ratio of polynomials. But look at the outcome of the graph. It doesn't look exactly like a quadratic because there's not just a parabola. This middle one has some parabola type characteristics, but it's not a parabola. The inverse variation, I can see where the branches are, but they're not exactly like inverse variation either because they're both topside. So it's not going to act exactly like inverse variation. It's not going to act exactly like the polynomials, but it does carry those characteristics. Today, we're going to start talking about how do we find all of these characteristics, and then by the end of the week, we'll be able to graph a full rational function with all of its characteristics. So today, I want to start with one of the key inverse variation characteristics, and that is the vertical asymptotes. All right? Vertical asymptotes. You can tell that there are vertical asymptotes in this particular graph. You can see right here at around, it looks like -1/2, there's some kind of vertical asymptote. And then over here around 7 appears to have a vertical asymptote. And so as always, just with like our inverse variation, the vertical asymptotes are imaginary lines, but they are what the graph is approaching. You can see this branch is approaching -1/2. This parabola type looking thing is approaching -1/2. It's approaching 7, and this branch is approaching 7. So they still have vertical asymptotes, and they still have vertical asymptotes for the same reason that inverse variation does. We cannot divide by 0. That's just hardstone math. You cannot divide by 0. So whenever the polynomial in the denominator is equal to 0, that's where a vertical asymptote is going to appear. So it's important to note, again, the cause of vertical asymptotes is because the denominator cannot equal 0. We're not going to allow the denominator to equal 0, and so that's how we find our vertical asymptotes. So to find the vertical asymptotes of a graph, what we want to do is we want to take whatever polynomial is in the denominator, we want to set it equal to 0, and we want to solve it. So in this case, I've got 2x squared minus 13x minus 7 is equal to 0. And this is a quadratic, so I need to remember all of my rules for quadratics. Quadratics I can solve by several different methods, but like we mentioned last week when dealing with rational functions, our go-to is going to be to factor first. So the first thing I'm going to try is to factor it. So I'm going to try and factor 2 times -7 is -14, and two numbers that multiply to equal -14, but add to equal -13 are -14 and 1. So when I go to use my area model and go backwards, I've got 2x squared and -7, but I know this was -14x and positive 1x. So here I have 2x in common, here I have 1 in common, here I have x in common, and here I have -7 in common. So then this factors to be 2x plus 1 and x minus 7. And now I notice that my factors equal to 0. So 2x plus 1 equals 0. Subtract the 1. 2x equals -1. when I divide by 2, x is equal to negative 1/2. And if you look at our graph, we had seen that that's where the vertical asymptote was. This is actually the equation of that line. Don't forget, the equation of a vertical line is always x equals a number. So the equation of this vertical asymptote is x equals negative 1/2. And then over here, when I set this equal to 0, I get that x is equal to 7. So that was this asymptote. X is equal to 7. What you're going to find when you actually do start trying to graph these functions, the asymptotes are the things that we have to find first. That's how we guide drawing our curves, because most of the points on this curve are infinitesimally small or weird fractions. And so it's not like you're going to find exact points to figure out much of the shape of this. The asymptotes are what give us the shape. And so the first thing we're going to do when we start to try and graph a rational function is we're going to want to find all of the asymptotes. So for this particular polynomial, you factor the denominator, set those equal to 0, and you do find your asymptotes. But you also remember that not all quadratics have real solutions. If the quadratic that's in the denominator has imaginary roots, if it's imaginary numbers where it's equal to 0, that means that particular inverse variation does not have a vertical asymptote. That means that it actually can be all of the numbers in the denominator. Nothing is getting left out. So you don't have to have a vertical asymptote. You only have a vertical asymptote if there is a possibility that the denominator can be equal